I hope that everyone already, learned something about a basic Hamiltonian of the solid state system, which consists of, say, electron interaction and electron-ion interaction, and also ion-ion interaction. And we introduce, we review the basic concept in solid state by telling you this Bloch theorem and energy bands and Fermi surface and this periodic nature of the solid state. So that's all review. And today we will start the advanced topic in so-called advanced solid state. Namely, we will introduce a new concept in solid state, which we will call this quasi-particle concept. So let me just tell you what is this, and we will discuss that in more details later. All right. So elementary excitation in solids. Please read David Pine's book, Elementary Excitation in Solids, which is out of print, but you may be able to find a copy in our library. This is a very useful elementary excitations. So this is the very new concept to all of you, and because this kind of objects, elementary excitations, are very important, and they are important to both theorists and experimentalists, because all we care about the solid states are mainly about this low energy, low temperature excitations. So this is the low temperature, low energy excitations in solids. And they often carry quantized excitation energy. And in many cases, they are long-lived. So we will discuss this in more details in a moment, but let me just very briefly tell you what it is. So this is, driven by thermal fluctuations in quantum mechanical many-body system, where the thermal energy excites some of the electrons and some particles that they get out of their energy levels and go to excited states. And that excited states are not far away from their ground states. Okay? So at low temperatures, many interesting properties come from exactly those low energy excitations. Okay, so almost all interesting physical properties are from those elementary excitations. So interesting, I mean this kind of a charge or spin kind of a properties. For example, this charge transport shows some very interesting quantum mechanical properties, or the spin or magnetic properties. And they are called elementary because they're made of quasi-particles. So this is also a very important concept in solid states. So I haven't defined this quasi-particle yet, but we will in just a moment. So to summarize, these elementary low temperature, low energy excitations often show some kind of a particle-like properties, namely their energies are quantized, just like photon. Okay? So we can count the photon energy by counting the number of photons. Okay? So likewise, there are elementary excitations in solids which consist of many photon-like or particle-like objects which carry quantized energy, and that quantized energy could be detected in experiments. And most of the interesting properties come from those quantized quasi-particle energies. So they are called elementary because they are elementary, just like elementary particles, So how many quarks do we have in nature? 6, right? So the proton neutrons are made of quarks, quark. Okay, so they are called elementary particles. And in solid state, we have elementary particles, and those elementary particles are called quasi-particles. So let me just classify these terms of elementary excitations, there are two commonly used terms. One is called collective excitations. Another is called quasi-particles. But depending on the reference textbooks, people may just mix all these different words when we talk about elementary excitations. Sometimes we call this quasi-particles. Sometimes we call this collective excitations. Sometimes we use quasi-particles to actually explain these elementary excitations. But the basic idea is the same, that there are fundamental elementary particles called quasi-particles exist in solids at low temperatures, which give rise to very rich quantum mechanical phenomena in low temperatures. And we should study these quasi-particle excitations. And this is the reason why we should apply the second quantization approach, because we could count the particle number. So let me just define this collective excitations. So as an example, this phonon, plasmons, and polarons, and magnons, and so on. Okay. So sometimes we call all these nouns quasi-particles, but some people call this elementary excitations. We could use these terms with equal footing. So this term quasi-particle is reserved in many textbooks for the electron-hole pairs in metals. So by the way, so we will give you more detailed explanations about this different collective excitations, such as phonons. You know what phonon is, and plasmons, and polarons, and magnons as we go along. Okay, so all these nouns are elementary excitations in solids in different contexts. Some of them are charge excitations, some of them are spin excitations, and some of them are simply just oscillations of the ion. And this quasi-particle concept sometimes is reserved for the electron-hole pairs in metals, but in the presence of weak Coulomb interaction. But of course, we could also call this interacting phonons as quasi-particles, but we can also call this magnons as quasi-particles. All right, so don't just be picky about these terms, but those terms just refer to the same thing, the same physics, that those objects come from quantum mechanics and also many-body physics. Okay, quantum mechanics plus many-body physics will lead to those interesting low-temperature excitations above the ground state, and those excitations are particle-like, and they carry quantum energy of excitation energy. And the point to study this is that all these low-temperature behaviors of solids are determined by those quasi-particles or collective excitations, right? So if you are experimentalist and what you measured in the lab, they are what you measured, okay? What you watch, well, these phenomena that you should pay attention to. Any interesting properties must come from some of them in the list. Namely, all these interesting and novel properties in solid state, the low temperatures, are here. And in other words, this is the focus of a solid state. Okay, so you may not be aware of this importance of the quasi-particle, but you should know now that all you measured, all you can think of in theory or in experiments are nothing but quasi-particles or elementary excitations. We don't care much about the high temperature, room temperature properties. Of course, there are some phenomena very interesting occurring in the high temperature regime, but not so much. Okay, so the most challenging and interesting aspects of this quantum mechanical solid state problems are all at low temperatures. And at low temperatures close to 0 Kelvin, these quasi-particles play a major role. So we need to understand those particles first. Okay? So this is a very important for all of you. No matter what experiment theory that you're studying, you should always learn this. Okay? You cannot escape this. Okay, so that's one thing. The second thing is that how do we understand this or study this? We first quantize their energy and we count the number of these quasi-particles. So the solution is straightforward. First, we should understand their quantized energies. So we need to have the Hamiltonian which could represent the behaviors of these quasi-particles, and we should quantize their energies. And we should find out their energy levels in a quantum mechanical sense. Then we know that each particle carry a single quantum unit of some energy. We call the quasi-particle energy. Okay? And the total energy of your low temperature solid state system is nothing but n times the energy of a single quasi-particle, right? So the total energy is nothing but n h bar omega. So the most interesting phenomena in low temperature solid state is excitation of a single quasi-particle. So you kick one quasi-particle out of your system, or you absorb some integer number of a quasi-particle in your system. So either you absorb or you emit a single unit in quantum energy of these quasi-particles, you will see some kind of energy associated with that transition between different levels of quasi-particle. And therefore, the system can be described by simply counting how many quasi-particles are there in your system. Okay, so the whole problem reduces to simply just count how many, because there are not so many. Okay, so you will see the reason why there are not so many quasi-particles at low temperatures. So for the obvious reason that at ground state there is no excitations at all, so that there's no quasi-particle available at zero temperature ground state. But if you simply just increase the temperature a little bit, then some thermal energies is going to kick some quasi-particle out of their stable orbits or levels. So you will have a small number of quasi-particles at very low temperature. Okay, so therefore, instead of solving the Schrödinger equation for each individual atoms or electrons, and that individual electrons and atoms is of order of 10 to the 23rd, that many atoms. So that's one way to understand the solid state. And a more efficient way, and probably this is the only way that we could study systematically the low temperature solid state, is to count the particle number, because we know how to count them in quantum mechanics. And secondly, there are not so many. So it's controllable. We can really count each quasi-particle one by one when we study some of the interesting processes in solid state. So theoretically, we can count the number of quasi-particles, and experimentally what you will see is really this excitation of these quasi-particles. So you can really see and observe the transition between spinning the body levels from, say, quasi-particle to quasi-particle, right? Okay, so you can really count the quasi-particle number in experiments. And so you will see the reason why we need to take this path instead of solving the Schrödinger equation for that many electron atoms, which is mission impossible. So, but modern solid state physics tells us that while you don't need to do that, you simply need to just count the quasi-particle number. That's all. Questions so far? Yes?
How can we define a weak or strong Coulomb interaction?
Okay, good question. So I haven't defined what I mean by weak or strong, but I imagine that this weak Coulomb interaction will not change your ground state substantially. So qualitatively speaking, this is my definition of weak. But more quantitative definition of a weak or strong, we can discuss that later. All right. So the so-called weak interaction is also very important concept here. Is that in, say, ordinary metals or insulators, the Coulomb interactions are not so large. Okay, in many cases, they are not so strong. So, the free electron gas model is actually a very good approximation to the realistic weakly interacting Coulomb gas, so-called Fermi liquid. So we will introduce the concept of Fermi liquid in just a moment. So in the Fermi liquid picture, the electrons that live in that periodic potential, which is assumed to be a weak Coulomb potential, can be considered as nearly free electron gas. Okay, so all this free, the predictions from the free electron gas are still valid in the presence of weak Coulomb interactions. So we will talk about that in just a moment. In that case, then what we know for free electron gas could be directly mapped onto this weakly interacting, say, Fermi liquid. So any other questions? Yes?
Can I call electron hole pairs excitone?
Well, it is related to the excitone. Good point. But here, we do not intend to study kind of a bosonic nature of an electron hole pair. What we emphasize here is the excitations of electrons nearby the Fermi level that are kicked out of the inner shell of the Fermi sphere and become the free electron. But that free electron is connected to the hole that the original electron occupied. So we call this electron hole pair. But I'm just about to introduce this electron hole pair. So let's just study this phenomena called the electron hole pair. So the example is precisely electron hole pair. So we all know that the free electron gas show a spherical Fermi surface, right? So this is your Fermi surface. And there are many K points in the sphere, and each point represents individual, say, electron level in this free electron band. You know that this is the band structure of the free electron gas, which shows this quadratic dispersion, and each energy level allows 2 electrons to occupy it, right? So that's the free electron gas. And for a partially filled band, you get metal, and electrons are freely moving, so they can conduct. So this is the reason why you get the metal. But now imagine that we have some Coulomb interactions, and we have a finite temperature. So at 0 temperature, all states within the Fermi sphere are occupied, and all the states above the Fermi sphere or out of the Fermi sphere are completely empty, right? So you could sort of use this Fermi-Dirac distribution to describe such phenomena. And this is the particle number as a function of the energy, and there's a jump right here at the Fermi level at 0 temperature that the occupation starts to jump from 1 to 0 right at that Fermi momentum or Fermi energy. So above the Fermi energy, no electrons can occupy it here. So all the states are completely empty, but below this Fermi sphere, and all the states are occupied, fully occupied. So this is at 0 temperature, Fermi-Dirac. So you know very well the Fermi-Dirac, right? So the F is what? Epsilon minus mu plus 1. And mu is called Fermi energy. So this surface of this Fermi sphere corresponds to this Fermi energy. And Kf squared is actually Kfx plus Kfy squared plus Kfz squared. Okay, so I assume that everybody is familiar with this, but this is so trivial, right? So nobody move. So that's not interesting. So let's just turn on some temperature. At the finite temperature, say just a slight increase of temperature above 0, and you will see that some of the electron states can actually be empty, and some of the electrons within such a ring, inner shell or outer shell ring, relative to the Fermi surface, will experience some kind of excitations. So that's what we call this elementary excitations. So for all the states that inside this orange sphere, they're all occupied. However, some of the electrons, say here, within the Fermi surface, but inside this inner shell ring, where this electron can actually be kicked out of their home, and this electron can actually get excited and become an excited state electron. Okay, and the energy that excited electron could actually have is within the window of KBT above the Fermi surface, and likewise within this window about KBT below the Fermi surface, that electrons are easily kicked out of their homes. Okay, so but this is just a rough estimation of this kind of elementary excitations. There's no sharp definition of this orange curve or orange ring. It's just a kind of an order of magnitude estimation that for the electrons living inside the Fermi sphere, but within this ring, and these electrons are very active electrons, and they could be kicked out of their leveled and become excited state electrons, so leaving behind a hole in their original levels. But we know that this electron kick out of the Fermi shell comes from the electrons or inside the Fermi surface, but now it becomes a hole because this electron is gone. Okay, so we call this electron hole pair. Okay, so you can imagine that for ordinary metals, this kind of electron hole pair, be easily seen because of the thermal excitations. And let me remind you the Fermi-Dirac distributions. So why there's a ring type of volume or thin shell near this Fermi surface that allow the electron to get excited, while the reason is Fermi-Dirac distribution. So you know that from this finite temperature Fermi-Dirac distributions, there are some probabilities for electrons that just order of KBT that could actually move to the states above the Fermi surface. The states above the Fermi surface of an amount of KBT are not completely empty. So there are some finite probabilities for the states above the Fermi surface, which shows electron populations. So this kind of a step jump of the 1 to 0 transition at 0 temperature becomes a crossover. A crossover refers to the fact that this kind of a transition, evolution, is actually a smooth transition. It's not a jump. Okay, so it's a very smooth crossover, from 0 to 1 or from 1 to 0, so that you have some finite probability below the Fermi surface that electrons can actually go out of the Fermi surface and become excited states, and that presumably empty states at 0 temperature now have some finite probability to have excited states to populate. Okay, so this physics is what we call the electron-hole pairs in ordinary metals. And you can see that the reason why we only need to count a handful of quasi-particles is that, so what about the remaining part of electron states inside the sphere? Well, they are very inert, inactive, they don't participate, but strictly speaking, this tail is actually very long. If you look at this Fermi-Dirac at final temperature, that there is just a tiny little bit probability at inner core of a Fermi surface that electrons can actually kick out of the Fermi surface. But that probability is extremely low, so we don't care about this tiny little bit probability, okay, inside this Fermi sphere, but we only care about the states at order of kBt below and above the Fermi surface, and that's the key point. So if you ask, how do I define this? Well, there's a crossover. Well, there's some finite here. Well, whatever way that you should define, this kind of a smooth crossover phenomena always exists. So no matter what kind of convention we use to define this narrow window that allows the elementary excitations, that's just a convention. But the physics is there. And the physics is that these electrons are very mobile and active, that they can be kicked out of their levels and become the excited states, leaving behind a hole. There are many such electron-hole pairs living in a low temperature metals. But how many electron-hole pairs are there? So as I mentioned, not so many. So why are there not so many? Because if you are in the 0 temperature limits, of course there is no particle-hole pair. That's for sure. Okay? You simply just infinitesimally just turn on the temperature, and you can imagine that this number of electron-hole pairs definitely just restricted to the small number of these quasi-particles. And the rest, the remaining part of the electron states, well, you can throw it away. You could disregard. You don't care about this. Just put in the black box. But you can only focus on the states that are relevant in the experiments. And these regions are the most important regions in your measurement or your theoretical understanding. And there are simply just a handful, not so many electron-hole pairs available at low temperatures. So it is a straightforward manner to count those. So this is the way we understand the low temperature solid state physics. We should count the number of electron states in excited states at low temperature limit. And so, but of course, this is just one example to show that there is such a kind of a quasi-particle excitations. But I haven't included the Coulomb interaction yet. So here I simply assume that all electrons are free. But imagine that those excited state electrons can actually interact by Coulomb force with the other electrons, either inside or outside of the Fermi sphere. But this electron-hole pair picture allows us to understand the, so-called Fermi-liquid resistivity in ordinary metals, that resistivity for ordinary metals behaves as T squared as T goes to 0. So we will come back to this in just a moment. So here I'm just telling you that this electron-hole pair concept is the only way that allows us to systematically understand the solid state physics at low temperatures. And we know they exist, and there are not so many of them. and we can count them one by one, and we know the quantized energies of those particles. So that sounds simple, but not so simple at all. Good. So I guess that's probably enough for today, because we don't have time to discuss this electron scattering by Coulomb, and which leads to this T-square behavior resistivity, which you could take a look at the arch curve fermion. For example, I don't remember which chapter, but you could look at this. Okay, so please keep in mind this picture. We will repeat that picture over and over and over again. Okay, so this picture should be imprinted in your brain, in your head, millions of times until you remember this picture. And this is extremely important physical picture of what happens for weakly interacting electron gas. So far, so good. Any other questions? Yes?
As you mentioned, when the system is subjected to the temperature, so it is related to the collective excitation. So you also mentioned that we can calculate the number of particles. So is there any way to differentiate among those collective excitations?
So we don't call this electron hole pair the say collective excitations. So they just randomly got kicked out of the Fermi surface, right? Okay, but we will come back to this collective excitations in this say phonons, especially plasmons and also meganons. So these objects or quasi-particles are truly collective motions because of many-body effect that all the electrons are dancing in the same period, same frequencies. But this electron hole pair, so they are not so much correlated from one pair to another. So it's kind of uncorrelated, but still they are elementary excitations. So a good question. So we will talk about this collective motions. But here we don't see that because they are simply individual electron hole pair that are kicked out of the Fermi surface because of the thermal effect. Yeah, so you could consider all these levels are quantized level, right? So there are many levels here. Okay, just like here. So this is the Fermi surface, right? So I can consider a particular level. There's an electron sitting here, and they actually got kicked out of the Fermi surface and become another say electrons occupy a particular level. So there, of course, is a level space, spacing between these two levels, right? So therefore, consider those electrons energies, excited state electrons. Simply just, we will calculate this later, okay? Simply just the difference between these two levels. Okay, of course, they are quantized. Even all these levels, inside or outside of a Fermi surface, are also quantized because remember, this K in the free electron dispersion takes a quantized value in a finite size system. So all energy levels are quantized. So you could actually count because you know the energy, and they are all quantized. Good. Any other questions? Time is up. And again, please try to read the first 1 or 2 chapters in David Pine's book, Elementary Excitation in Solids. So I request that all of you should read and see these pictures there. So I don't count this homework, but this is an unofficial homework. Read David Pine's book on this topic. Okay, so I will ask you one by one next time when I see you whether you have read this David Pine's book, and if you find this kind of a picture there. Good, enjoy this lecture.